The next rule we want to develop is the derivative of the power function. This one will come up more often than any other, so it's a good idea to really understand it. All right, the way we're going to construct this is we are going to look at derivatives of particular power functions until we think we can confidently deduce the pattern. All right, so we're going to start with the derivative of f of x equals x. And we're going to use the formal definition, except this time we're going to use this definition of the derivative. We're going to find the derivative at a instead of x equals to the limit as x approaches a of f of x minus f of a all over x minus a. This is the form that we're going to use in this particular case. Okay, so if we apply this formula to this function, we get the limit as x goes to a. F of x is just x. F of a is just a. So x minus a over x minus a equals 1. And so if f of x equals x, then f prime of x equals 1. Okay, because this is true for any value a, and so it's true for any x value. All right, now let's look at f of x equals x squared. So let's find the derivative at a of this particular function. So it's the limit as x approaches a of x squared minus a squared all over x minus a. Because f of x is x squared, and so f of a would be a squared. Now if I factor, I get the limit as x goes to a of x minus a times x plus a all over x minus a. Those cancel. Now I can do direct substitution and I get a plus a or 2a. And since this is true for any a value, this tells me that the derivative of f of x equals x squared for any x value is 2x. Okay? Let's do another one. Let's look at f of x equals x cubed. All right. F of x equals x cubed. All right, so then f prime of a is going to be the limit as x approaches a of my function f of x, so x cubed, my function evaluated at a, so a cubed, all over x minus a. Now this also factors, this is the difference of two cubes, so it factors to x minus a times x squared plus ax plus a squared. You may have to go back and review the difference of two cubes. Divided by x minus a. These cancel, and I'm ready to do direct substitution. And I get a squared plus a times a is a squared plus a squared, which is 3a squared. This is true for any a value, so it's true for any x value. So f prime of x is 3x squared. And right above here, let's write what we already know. If f of x equals x, f prime of x equals 1. If f of x equals x squared, f prime of x equals 2x. All right, let's do another one. Let's do f of x equals x to the 4th. You may think you already know the pattern, but if not, keep watching. So the derivative evaluated at a is the limit as x approaches a, x to the 4th minus a to the 4th, because that's f of x. That's f of x, f of a, all over x minus a. This also factors to limit x to a, x minus a, x cubed plus ax squared plus a squared x plus a cubed, all over x minus a. And guess what cancels? The x minus a's. And I'm ready for direct substitution, so I get a to the third plus a times a squared, another a to the third, plus a squared times a to the third, plus a to the third, or 4a cubed. This is true for any a value, so it's true for any x value. So that tells me that if f of x equals x to the fourth, so we can all see, f prime of x equals 4x cubed. Now, what do you think is going to be true for f of x equals x to the fifth? Well, you would be right if you guessed that it is going to be 5x to the fourth. Let's just check one more time by taking the derivative the long way of f of x equals x to the fifth. I'm just going to put this right on top so we can keep things lined up. So for f of x equals x to the fifth, f prime evaluated at a is the limit as x goes to a of x to the fifth minus a to the fifth all over x minus a. And I'm guessing you now know how this factors. Limit x to a, we pull off an x minus a, and we are left with x to the fourth plus ax cubed plus a squared x squared. Move that over a little bit. Plus a cubed x plus a to the fourth all over x minus a. All right, so it's important that we understand this. When we put direct substitution in here, we are going to get a bunch of a to the fourths. And the question is, how many a to the fourths do we get? Let's count. 1, 2, 3, 4, 5. So this is equal to 5 a to the fourths. All right, I think we're ready to generalize for an arbitrary integer. So let's say f of x equals x to the n, where n is a positive integer. All right, then f prime of x equals, f prime of a equals the limit as x approaches a of x to the n minus a to the n all over x minus a. Now here, if you have been paying attention and have deciphered the pattern, this factors to x minus a, and what do you think's left behind? X to the n minus 1 plus a times x to the n minus 2. Notice up here I went down in powers of x all the way till I had no x's, and I went up in power of a's all the way till I got to a to 1 less power than my original function. So this next one would be a squared x to the n minus 3, and I would keep going all the way to, let me move that over a little bit. I should do my last two terms. So the term right before the last one should be a to the n minus 2 x plus a to the n minus 1. And how many of these do we have? We should have, if I plug in a for all of the, all over x minus a. So I can see right here that I have n minus 1 terms that have a, and then this term, so I have n terms of a to the n minus 1. So this equals, what did I say? N terms of a to the n minus 1. Again, this is true for any value of a, so this tells me that if f of x equals x to the n and n is a positive integer n, then f prime of x equals n times x to the n minus 1. And so what we learned, at least in that illustration, for positive integers, that the derivative of x to the n is equal to n times x to the n minus 1. And actually what is true is that this derivative holds for any real number n that's not 0.